Απόψε έχουμε την ευχαρίστηση να έχουμε μαζί μας την καθηγήτρια του Technical University of Civil Engineering στο Βουκουρέστι της Ρουμανίας, την κυρία Loretta Batali. Την κυρία Loretta Batali, χάρη κυρίως στο ελληνικό μας γραμματέα, τον Γιώργο Μπελόκ, έχουμε αναπτύξει μια εξαιρετική σχέση, η οποία επεκτείνεται και πέραν των προσώπων μεταξύ των δύο ενώσεων της Ελληνικής Ένωσης Γεωτεχνικής Μηχανικής και της αντίστοιχης Ρουμανικής Ένωσης Γεωτεχνικής Μηχανικής. Και η κυρία Μπατάλη μας ενημέρωσε ότι θα βρίσκεται στην Αθήνα και είχε την καλοσύνη να αποδεχτεί το αίτημά μας, παρά το πολύ βαρύ πρόγραμμά της, να έρθει και να μας δώσει μια ομιλία πάνω στην πολύ σπουδαία δουλειά που κάνει, στην Επιτροπή η οποία βρίσκεται για τη δημιουργία παραδειγμάτων για τη νέα γενιά του ευρωκώδικα, και αυτό είναι που θα μας παρουσιάσει απόψε. Η κυρία Μπατάλη έχει μια μακρά σχέση με τη δημιουργία ευρωκωδίκων και εκεί είναι η σπουδαία της εμπειρία την οποία θα μας δείξει απόψε, και κυρίως ως editor του Technical Group on Design Examples using the Second Generation Eurocode. Έχει κάνει αρκετή δουλειά για τη δημιουργία παραδειγμάτων, τα οποία μάλιστα θα μαζευτούν σε ένα συγκεκριμένο τόμο, στον οποίο είναι editor η ίδια με co-editor το γενικό μας γραμματέα τον Γιώργο Μπελόκα, η οποία έκδοση θα δημοσιευτεί σύντομα από το Joint Research Council της Ευρωπαϊκής Ένωσης. Ενώ επίσης από την 1η Πρώτου του 2025 η κυρία Μπατάλη θα είναι αντιπρόεδρος στην Επιτροπή SC7 του Ευρωκώδικα 7 της Τεχνικής Επιτροπής TC250 του Ευρωπαϊκού Οργανισμού Τυποποίησης. Κατά συνέπεια, νομίζω ότι απόψε έχουμε μαζί μας τον καταλληλότερο άνθρωπο να μας μιλήσει για τη δεύτερη γενιά των ευρωκωδίκων. Και τώρα θα πω και δύο κουβέντες στα αγγλικά για την προσκεκλημένη μας. Dear Loretta, I have been saying many beautiful things about you and how important you are in the development of the second generation of the Eurocode. So, without further delay from me, I kindly ask you to come to the stand and deliver your lecture. Thank you very much.
Thank you, Michalis, and thank you to all of you for inviting me, delivering this lecture, and for coming and listening to me live here today. So, yeah, I will try to give you an overview of the key changes and what is the evolution of Eurocode 7, with a special focus on file foundation design. So, I will start by saying that this revision of the Eurocode 7 for arriving at the second generation of Eurocode 7 had several objectives. First of all, obtaining at the end a standard suitable for all common design cases to improve the ease of use. We are not very sure that we obtained this at the end, but we tried. We did our best to do it. To obtain a better harmonization, and also this, it is not really a harmonization, and when we are speaking about the different practices across Europe to other countries, as for example we had some weeks ago a webinar of several hours with Asian countries, they are not understanding at all how that we cannot understand each other and we cannot harmonize for real, let's say, our design practices. But it is a little bit improved. And also to have some developments, as for example, including numerical methods, the probabilistic design based on reliability concepts, to include new geotechnical structures, and also some aspects regarding sustainability, as for example, thermoactive geostructures, piles, and diaphragm models. First of all, there was a reorganization, and as you already know, in the current Eurocode 7 we have now two parts, one for general rules for geotechnical design and part 2 for ground investigation and testing. And together with these two parts of Eurocode 7, the first generation I mean, there is also need to consult and to work with Eurocode 0, which is setting the basis of the structural design. Now in the second generation of Eurocode, and I will try to have something like this. Yeah. In the second generation of the Eurocode, we need now, of course, Eurocode 0, which is called Basis of Structural and Geotechnical Design. And this is a very big achievement for our profession, to have our specificity of the geotechnical design in Eurocode 0. And we must acknowledge the merit for this, to Andrew Bond. And now we have three parts. Part 1, which is general rules. Part 2, it is called now ground properties. And part 3, geotechnical structures. So now we have to work with 4 documents in our toolbox, let's say. Oh, it's not working anymore. It is so dark that now I'm not seeing the keyboard. Okay, thank you. I will try to manage it. Okay, so what are the new developments now, the new concepts in Eurocode 7? First of all, now we included rock engineering everywhere. That means that the ground can be composed either of soil or of rock. And everywhere in the code, in the 3 parts of the code, we are referring also to rock engineering. Geotechnical category has been completely refurbished, and now is a combination between the complexity of the structure through the consequence classes and the complexity of the ground, and we have a new concept of geotechnical complexity class. Those 2 elements combined are giving the geotechnical category. The representative value of the geotechnical parameter is another improvement and clarification in the second generation, and now we have 2 ways to determine the representative value of a geotechnical parameter, either as a cautious estimate as it was before, or by statistical approach. As I said before, the part 2, it is now called ground properties instead of ground testing and investigation. That means that we are referring to the main users of this design code, which are the designers. And the designers are looking mainly for parameters and properties, and not what is the test and how I can use this test for deriving a geotechnical parameter. So there is now a focus to input for design. What is the input for design? Another new feature is the ground model as the result of the geotechnical investigation phase, and the geotechnical design model, which is the input for the geotechnical design phase, which is the second phase in any project, any geotechnical project. Yeah. We also have some new technical developments in part 3, and we have now included file groups and file drafts, and I will refer in this lecture today to this. Also reinforced fields, rock bolts and soil nails, ground improvement techniques, and also measures for groundwater control. All these are completely new, and they were not included in the first generation of the Eurocode 7. So, as I said before, now we will need in our toolbox 4 documents. What can we find in each of those 4 documents? In Eurocode 0, Basis of Structural and Geotechnical Design, we will find general design principles, consequence classes, and consequence factors applied to actions. So the consequence factors, which are trying to make a differentiation in the reliability applied to different categories, let's say, of importance structures, can be applied either on actions or their effects, or on the materials, that means on the ground parameters, or on the resistances. So here in Eurocode 0, you will find the consequence factors applied to actions. Also, we will find partial coefficients for actions and effects of actions, and also what are or which are the verification cases for ultimate limit states. So all this will be found in Eurocode 0. In Eurocode 7 now, in part 1, general rules, we will find the geotechnical categories, the new ones, the representative values of geotechnical parameters, and here we have the two ways for determining it, either as a characteristic value, that means by statistical methods, either by nominal values, which are the cautious estimates. The geotechnical design model, how to develop it as the first part or the first step in our geotechnical design. The partial factors on ground properties, gamma m, which are applied to the ground characteristics, and the consequence factors that are applied either to the material, Km, or to the resistances, Kr. So all these are found in part 1 general rules. And also, what are the ultimate limit states and serviceability limit states for the geotechnical design. All this will be in part 1 general rules. In part 2, ground properties, we will find the ground model, which is the main output of the geotechnical investigation phase, and we will find the ground model in the geotechnical investigation report. And also, we will find information about the derived ground properties. That means those values of the parameters that are derived either from laboratory tests or from in situ tests. And also information about laboratory and ground investigation, which are used for deriving the geotechnical parameters. And in part 3, for each geotechnical structure, we will find the same structure of information. That means the conditions imposed for ground investigation, some aspects regarding the groundwater, how to consider it in relation to each geotechnical structure, principles for geotechnical analysis, verifications for ultimate limit states and serviceability limit states, values of the partial coefficients applied to resistances, gamma r, are to be found in part 3 for each geotechnical structure, model factors, gamma rd, which are applied in order to correct certain theories or certain formulae and so on that we are applying when we are calculating something, the resistances, and also a new chapter, implementation of design in execution, because finally the success of a project it's also relying on a good execution. So there are some provision regarding how to implement the design in execution, testing, and also reporting for the geotechnical design phase. I have problems because it is so dark that I cannot see anything here. So, no, it's okay. I am managing. I will keep my finger on the right key here, not to lose it anymore. So, this is an overview of the geotechnical structures that, thank you. Geotechnical structures treated in part 3. So, we will find here slopes and cuttings and embankments, spread foundations, piled foundations, retaining structures, anchors, reinforced field structures, which is completely new, soil nailed structures, also new, rock bolts and rock surface support, new, ground improvement, also a new chapter, and groundwater control measures, another very new chapter. So all these clauses or chapters are to be found in part 3 of Eurocode 7. So, I I will refer now only to some of the key changes in part 1 and part 3. I will not refer today to part 2. I would like to emphasize the new concepts regarding risk mitigation using the new geotechnical category. As I said before, the geotechnical category was completely revised, and now is a combination between the consequence class and the geotechnical complexity class. So here is the importance of the structure, and here is the complexity of the ground. And you can see here how those two are combined in order to obtain the three geotechnical categories 1 to 3 for different consequence classes and different complexity classes for the ground. So in EN 1990 we will find the consequence class. In EN 1997 we will find the geotechnical complexity class, and also Eurocode 7 will teach us how to combine these two information in the geotechnical category. What are the consequences of a certain geotechnical category? We will have a certain quantity of minimum ground investigation or a minimum requirement for the ground investigation, minimum validation of calculation models. So our calculation models, if they are not yet verified by our long time practice, we will have to provide some measures for validating these calculation models. And there are also other consequences that can be found in Eurocode 0, that mean the minimum design check level, minimum execution class, minimum inspection level, and minimum design quality level, which is related to the qualification and experience. So these are provisions, let's say, in Eurocode 0. And also in Eurocode 7, we will find the minimum amount of monitoring, which is related again to the geotechnical category. And of course, for higher geotechnical categories, we will have to fulfill more severe or more detailed requirements for monitoring. So all these are related to the new geotechnical category. Also, I mentioned the fact that the representative value of the geotechnical parameters is completely refurbished, because it was not clear in the first generation. It was said that the characteristic value should be a cautious estimate. How cautious? It depends on the designer, finally, on his or her experience and so on. So now we have this name, let's say representative value, which is either a characteristic value that is statistically determined, or a nominal value that is based on engineering judgment and based on the idea of cautious estimation. So we can choose what path we would like to follow, either by statistical means. That means that we need a minimum quantity of values. We will not apply statistics for 3 values, let's say, even though in theory it is possible, but this is not making sense. And whenever we need something else, we can use the engineering judgment, our expertise, our experience and so on, in order to derive the nominal value. And there is also another value of the geotechnical parameter, which is a best estimate value, and this is not including the uncertainties. This is not including a safety factor here. It is our best guess, let's say, of the geotechnical parameter, and this value will be used for prognosis or for back analysis when we are trying to make a back analysis based on a monitoring, for example. We will not use a value that is incorporating a safety, because of course we will not find a match with the values monitored on site. So this is also another thing that is now clarified. So we have representative, either nominal or characteristic, which are based on derived values of geotechnical parameters issued from laboratory tests for empirical correlations or from test in situ testing, and also from back analysis based on monitoring. Another new feature is the ground model. The ground model, as I said before, is the output of the geotechnical investigation. It is something that all of us we are doing. It is not new. It is new in terms of provision in the code, but we are all doing a ground model, either in our head or on a piece of paper or in a very nice form, let's say in a colored graph and so on. This ground model will be the base for the geotechnical design model, where we will make some assumptions, some simplifications, some details where it is needed, and so on. So the geotechnical design model will be developed at the geotechnical design phase in the geotechnical project. And in the geotechnical design model, we will have to put not only the lithology of the ground, but also the parameters that will be used in the design. And these have to be chosen by the designer. And each geotechnical parameter we are using in our design should be correlated with the limit state that we will verify, because we will not choose the same value for, let's say, a general or an overall stability analysis, or in a very local bearing failure, for instance, where we can have a weak area and so on. So there is a judgment behind all this, and the designer will do this. Of course, we are keeping the 4 methods of verification of ultimate limit state. That means by calculation, which is the main method we are generally using, and we are still applying the partial factors method, which is, let's say, a simplified reliability method. We have only one verification or expression to verify, which is the design value of the effects of actions, which has to be less than the design value of the resistance. And this is the general expression that we have to verify by calculation. And we have 2 possibilities here. Either to apply the partial factors on the materials, considering that the main uncertainty is on the ground parameters, and this is called the material factor approach, or to apply the partial factors to resistances, and this is called the resistance factor approach. It is just another name for the same thing that we were doing already this in the first generation. It is nothing changed, only the name, the hat, let's say. We still have prescriptive rules whenever it is considered to be suitable, predetermined, experience-based rules for design. Verification by testing, that means to perform tests to verify that the performance of a geotechnical structure is within the limits that were conceived in the project. And also the observational method, which is now a little bit more clear, and the code is giving some new provisions about the observational method. Now, having said all this, which is a very brief and general overview about the changes, I will go to the main topic of this lecture. That means, how are we designing pile foundations according to the 2nd generation of Eurocode 7. Here we have clause 6 in part 3, Eurocode 7 part 3, clause 6, and we can find here the scope and the field of application, and this time this will apply also to pile groups and pile drafts. Pile drafts were not included in the previous generation, but also to rigid inclusions, which are now treated by clause 12 in part 3 for ground improvement. This clause 6 will apply to all kinds of piles. That means displacement piles, replacement piles, and other type of piles. So we will find a more detailed classification in Annex C, Table C1, examples of piles in different classes, full displacement piles or partial displacement piles, and many technologies are given here for trying to orient the user, and also replacement piles, and any other type of pile should be in a separate category from these main three categories. As I said before, we need our toolbox with our 4 documents, Eurocode 0 and the 3 parts of Eurocode 7. I will not repeat what I said before, where to find what are to be found in Eurocode 0, but I will give you here an overview of the table with partial factors gamma F and gamma E for actions and effects of actions, and the verification cases. And here we can find permanent actions, pre-stressing variable actions, and in the permanent actions we are finding water, which is a separate category with another value of the partial coefficient, considering that there is less variability in the water or groundwater action than in the structural action. And also, of course, different categories, unfavorable or destabilizing, stabilizing, favorable, and so on. We can find here 4 verification cases. So we don't have any more design approaches, we have verification cases, and these are defined once more in Eurocode 0. So this is available for all kinds of design for any structure in civil engineering. We have VC1 for structural resistance, which is what we know already, with this exception of a smaller value for water. We have VC2 with 2 combinations A and B for static equilibrium and also uplift, which is of interest in the geotechnical design. And we have the geotechnical design with 2 possibilities, VC3 and VC4. In VC3, only the variable actions have a value different than one that is applied as action coefficient. And in VC4, we are applying the coefficients to the effects of action. So this is the former, I think, DA2 star, or something like this in first generation. So this table, it is found in Eurocode 0. In Eurocode 7 Part 1, as I said before, we can find all those information. And here we have provisions that are in addition to those provided by Eurocode 0, that ultimate limit state can be verified either by material factor approach or resistance factor approach. The values of the coefficients for the material factor approach, that means the partial factors applied to ground properties, we can find them in Eurocode 7 Part 1. While the partial factors applied to resistances, gamma R, are to be found in Eurocode 7 Part 3. And the partial coefficients for actions and effects of actions, as I showed you before, in Eurocode 0. And here is the table for gamma M. So the 2 sets of value that we know already, that means either we are not applying the incertitude to the materials, or we are applying it for the materials in the material factoring approach. And this first part of the table is more or less what we know already, but we have another part for rock material and rock mass, rock discontinuities, and for interface friction between the ground and the structure. And also you can see here in the second column, where we have values different than 1, the consequence coefficient Km, if this one is applied to the ground properties. And here we can see the values for the Km according to the geotechnical, the consequence class, 1.1, 1 for a geotechnical category 2, and 0.9 for the first one, the lowest one, consequence class. In part 3, pile foundations are treated by clause 6, and we will find there how to perform the ground investigation, what are the requirements, the geotechnical analysis of pile foundations, either by calculation or by testing, ULS and SLS verification, the coefficients gamma R, model factors, and we can find provisions for a single pile, pile groups, and pile drops. Okay, let's see what are the information regarding all this. So I will not refer to everything, but you will find some data about the zone of influence, which has to be considered when we are planning the ground investigation, the geometrical properties, and the actions. And there are details about actions, either permanent or variables, but also, and this is new, cyclic and dynamic, and also actions due to ground displacement. And for cyclic and dynamic actions, it is said that the adverse effect of cyclic and dynamic actions on the long term, either axial or transverse resistance of pile foundation shall be considered. And there are some examples here how to consider the stability diagram for cyclic and dynamic actions. And this is in Annex C, which is devoted to additional information regarding the pile foundation. Also, here you can find the minimum depth of field investigation for pile foundations. For a single pile, pile groups or pile rafts in soils or very weak and weak rocks, and pile groups or pile rafts in strong rock. And there are some minimum depth of the investigation that has to be fulfilled. And this is an NDP, that means a national determined parameter. And there are many, including the values of the partial coefficients. That means that every country in its national annex will be able to modify, if necessary, these values that are by default or they are proposed in the main code. Also, there are some provisions regarding materials, either ground concrete, grout, steel, or other materials that can be used in pile foundations. And for the ground, there is a list of field tests and ground parameters that are needed for the design of a pile foundation. In terms of actions due to ground displacement, there is also some new part. There are things about down drag, negative friction, heave, and transverse loading. And I will refer only to down drag in this presentation. And here there is a new aspect regarding a simplified approach that can be used, assuming what are the depths of the neutral plane. The neutral plane being the level at which we are changing the direction of the force, either downwards or upwards. So, it is said that if the pile settlement at ULS is higher than the soil settlement, the neutral point may be assumed at the ground surface, and in this case we can disregard the down drag for ULS. If on the contrary the pile settlement at ULS is much small, much less than a soil settlement. And also for SLS, the neutral point should be considered at the base of the compressible soil, which is this one, and we can obtain the upper value of the drag force considering in the calculation the full thickness of the compressible soil. And this is the formula for determining the representative value of the drag force considering this simplified approach. If not, so we don't want to consider this simplified approach, we can perform a rigorous interaction modeling in general, considering the neutral point according to the definition as the limit between the forces going downwards and upwards along the pile shaft. And also it is mentioned that the value of the position of the neutral point is not the same at SLS or at ULS. For the ground settlement called S-ground, this can has to be estimated, including not only the immediate settlement but also the consolidation and, if required, the creep. While the pile settlement, S-pile, can be determined either by analytical methods, empirical, numerical methods, or by an interaction analysis considering that the settlement of the pile will be equal to the settlement of the ground. And here it is the calculation scheme that is given in Annex C of Part 3 regarding the rigorous interaction model for downdraft. Also, please note the fact that the drag force, the rep, the representative value of the downdrag force, is not combined directly with a variable load. So either we should consider a combination of actions with the variable load or with the value of the downdrag. And here is for SLS, and here is the combination for ULS. So there are two different combinations, and we will not consider together the downdrag with the variable action, which I think is a modification, because at least in Romania we are always considering all the forces, including the downdrag for ULS. I don't know how you are doing now according to the first generation. Okay, for the geotechnical analysis now, how to determine the resistance, because we now know the actions and we need the other part, the resistance. We can use the four methods, but in general observational method is not commonly used for the design of pile foundations. We are mainly using calculation and testing, and also from time to time and in various countries the prescriptive rules. We have these prescriptive rules for pile design in Romania. And there are provisions regarding the resistance of single piles in compression, in traction, and for transversal actions. And here are some details about this. For axial resistance of single piles by calculation, if we are using the design by calculation, we can find in the code two methods. And these are, in my opinion, these have a name that is not very clarifying. Let's say not everyone is understanding the same thing from those names. The first method is the ground model method. That means that the ground properties are determined either by laboratory or by in situ test, and then they are used for calculating the resistance of single piles. The second method is the model pile method, and this is less understood, that it is based on individual pile resistance profiles determined from correlations with field tests, as for example con penetration test, pressure meter, SPT or other type, but mainly CPT and pressure meter. I'm sorry, here it is something that is hidden. but it is the normal, let's say, the used already formula that the compressive resistance, it is formed from the base resistance and the shaft friction resistance. And these are the general formulae that we are using even now. For the ground model method, there are some details in Annex C, C4, pile shaft resistance based on ground parameter, and there are some formulae given here how to derive the resistance, the pile shaft resistance, when we know the values of the ground parameters, that means friction, angle, cohesion, and so on. Sorry. And here it is I will go back just to show you that there are values. I can enlarge maybe. Great. For total stress analysis, this is the representative value of the unit shaft resistance for fine soils and silts. And here is the value of the same thing for weak and medium strong rock masses. So you can see here that everywhere we have included the rock. I have now to do it like this. Oh. And here is total stress analysis, again representative values of unit base resistance, the other components for fine soils and silts. And here are I would say the normal used formulae for computing the bearing capacity. And here are the values again for the base resistance in very weak and weak fine-grained rock masses. For the model pile method, there are some details in Annex C6 for CPT and C7 for pressure meter. And you can see here how to compute the axial pile resistance based on CPT profiles. And here are the typical value of this empirical cone factor for shaft resistance for coarse soils and silts in this table, and also how to determine it for clays, silts, and pits. And there are several zones that has to be defined on the CPT diagram, and this is the definition. I don't know how is your practice in Greece. I can tell you that in Romania we are rarely using CPT. We are using CPT, but since our lithology is not so soft, I would say, as in the Netherlands where CPT was developed, we are not basing mainly our pile design on CPT. In another annex, C8, I didn't include here the pressure meter, the annex for the pressure meter, because I don't know exactly if you are using pressure meter. We are not using. We only have one pressure meter in Romania. I'm not very sure that they are interpreting correctly what they are measuring. We don't have this experience. And we still have the design by prescriptive measures in Annex C8 with empirical values for base and shaft resistance only for bored piles in soils. So all these annexes, and this is something I didn't say, are informative annexes. That means that in your national annex, you can turn them mandatory, you can cancel them completely, or you can keep it as informative. Or you can replace them completely with some other thing that it is according to the Greek practice. And every country can do this. So here, for example, in Romania, we will replace this, that's for sure, because we are using different prescriptive tables for determining the bearing capacity of piles. And of course, it is very important, the design by testing. It is used everywhere. mainly using static pile load test for ULS and SLS. It is used for piles in compression and tension, and also it is allowed to use dynamic load test and rapid load test, but only for piles in compression at ULS. For the transverse, all those things were for axial resistance of single piles. For the transverse resistance of single piles, we can use either calculation or testing. In terms of pile groups, here we can use numerical, analytical, empirical, and also observed performance methods. And for the design of pile groups, we have to consider pile-soil and pile-pile interaction. And here is the definition of the ultimate compressive resistance of a pile group, R group, which is, and I will enlarge to see better, the minimum value between the sum of all the ultimate axial resistance of all the piles in the group, and R block is the ultimate vertical resistance of a block of ground which is bounded by the perimeter defined by the extreme piles. Yeah, so this is the whole group, including the soil which is surrounding the extreme piles, and this block pile plus the soil, the ground, it has a resistance which is called R block. So it's not necessarily the sum of the bearing capacities of the piles in the group. Also, in Annex C10, again an informative annex, there are some details regarding pile groups subject to axial tension. And there are three mechanisms that we should consider: the pull out from the ground, the lift of the total block of the ground, including the soil, and also a combined mechanism, a failure mechanism, pull out and lift off. And here we have a situation where we have also a layered ground, including sand and clay. So in this case, there is a block failure of a single pile, which is defined here, and for the evaluation of the block failure, there is a formula given for computing the representative weight of the ground block that we should consider in the calculation. And all these, again, are informative annexes or informative information. Another new thing is the pile draft, and this it is still very general in the code, because of course here we have several practices that were developed during the years. The general idea is to consider all kinds of interactions: pile soil, pile raft, soil pile raft. So this can only be done using numerical modeling and also some semi-empirical methods. For the numerical modeling, I said before that this is a new feature in the Eurocode 7, but here it is the reference in Eurocode 7 Part 1, paragraph 8.2. You can find two ways of performing numerical analysis using the partial coefficient method. So here we can find the graphical definition of all those interactions that are illustrated here by these arrows, and you can find here a very general formula of the resistance of a pile draft, which is the sum of the ultimate resistance in compression of all the piles plus the additional bearing resistance of the raft. It is very general, for instance. You can find some more, again, general provisions in Annex C, but not very detailed. It was a very big discussion about this, and different countries fought each other in order to include their practice, and finally we arrived at this very general situation, let's say. Okay, in terms now of displacement of pile foundations, there are some aspects treated in the code regarding the settlement and transverse displacement of single piles obtained from load tests or by analytical, numerical, empirical, or prescriptive rules, and also for pile groups and pile rafts. Calculation methods for pile group should consider the load displacement behavior of single piles as well as the behavior of pile group, of course, and also should consider the movement and the loading effects caused by the interaction between the piles and the interaction with the supported structure. In Annex C11, you can find a calculation model for the settlement of a single pile using load transfer functions. And here are some examples of load transfer functions that are included in this annex for the assessment of the pile settlement. And also for the lateral displacement, there are some models given for the deflection of the pile versus the pressure, and also the Py curves that are also included there in C12 annex. Another subclause is devoted to the confirmation of pile design by testing. And again, I don't know exactly how you are proceeding in Greece, but I will tell you how we are doing it in Romania and why this chapter is important for us. Because mainly we are not going up to the failure for the test. So they are testing piles in the structure, which will be used further in the structure. We have a minimum number of piles to be tested, and we are confirming the calculation, which are either done based on empirical methods or on analytical or on CPT whenever it is available. So in our case, there will be a validation of the design using static load test, but not up to the failure. So here are given, and it is again an NDP, the minimum quantity of load testing for confirming the design by testing in these conditions. For static load test, for ultimate pile load test, or for serviceability. So you can see here the numbers that should be fulfilled, and you can change it because it is an NDP according to your practice. Now that we know the actions and we know the resistances, let's go for the verification. How verifying now, including all those principles of the partial factors method. For the ULS, first of all, ULS verification for single piles, axial compressive resistance, we need to fulfill this verification. So the axial compressive compression force, the design value should be less or equal to the design value of the axial compressive resistance, including, if necessary, the cyclic degradation effect if we have cyclic or dynamic actions. And the design value of the resistance, RCD, is either the value of the representative value that we have determined already, divided by the gamma RC, which is the partial coefficient for the axial compressive resistance, and gamma RD pile, which is a model factor. And this is depending on the method that we use we applied for determining the bearing capacity. So some methods are more accurate, let's say, and they are approaching more to the values that will be measured, and others are a little bit far away. So with this, by this value, we are trying to correct, in fact, the accuracy or the precision of the methods that we use. These values are given in part 3 in this clause 6 we are talking about. And here you can see the values for the model factors. And you can see that this is depending if we applied by calculation, here is the word calculation in this table. You remember the two methods, ground model method and model pile method. And you can see here the model factors for ultimate pile load test, extensive comparable experience without site-specific pile load test, serviceability pile load test, and no pile load test, and limited comparable experience, which is of course giving a very high value of the model factor. In the model pile method, if we are using Menard pressure meter in compression and in tension, con penetration test, very low value because it is replicating, if you want, a pile, and profiles of ground properties based on field or laboratory tests, 1.2 in this case. So these are the model factors. And here are the model factors if we are using the method by testing or assisted by testing. So here we have model factors, fine soil, coarse soils, and rock, static load test, rapid load test, several types, dynamic impact test, wave equation analysis, and pile driving formulae. It is not permitted, some of those are not permitted in some cases for fine soils or for coarse soils. And these are the values of the model factors. And you can see, for instance, for dynamic impact test, quite high values. And here are the formulae that we have to use. For the ground model method, the representative value of the resistance of a single pile, it is equal to the calculated pile resistance based on ground parameter. But for the model pile method, we will use the correlation factor psi. That means we should use the minimum value between the ratio between the mean calculated value divided by the mean correlation factor, or the minimum calculated value divided by psi minimum correlation factor. And here you have the correlation factors, psi mean and psi minimum. And here is a thing that is new, the coefficient of variation. And I will show you at the end of this presentation some design examples to see how you have to consider it, because you need to verify the coefficient of variation of the various values you obtained in different points across the site, and these values are applied if the coefficient of variation is less than 12%. And if there are not less than 12%, you have to form clusters of points which have a coefficient of variation less than 12%. And you have here different values according to several possibilities, several numbers, various numbers of tests or profiles. So of course, if you have only one profile, the value will be higher, and if you have more than 20 profiles, the values will be considerably lower than the first values. If we are determining the representative resistance by testing, again we have something similar as before, considering the correlation factors for the mean values and the minimum of the measure values, but these values are determined by testing. So here you have the correlation factor psi for different various numbers of tests, and the correlation factors for static load tests and for rapid and dynamic impact tests, which are of course higher values than for the static load test. I should probably speed up a little bit. There is also some new feature about the structural resistance, including buckling, and there is a special annex C for this, and you can find there the theory of second order for verifying the buckling. I will not enter into the details. And here are the verification that we should verify for ULS for pile groups and pile drafts, and also here are the general verification formulae, and here are the how to apply the material factoring approach or the resistance factoring approach for pile groups and pile drafts. So here you can see for the material factor approach we don't have anything, any specific formula, because we will apply the gamma m factors to the ground properties, and after that we will use those values in the calculation. But for the resistance factoring approach, we will divide the value of the resistance of the pile group by the gamma r for a group of piles, and the appropriate model factor, which is related, as I said before, to the method of calculation, and also for the pile raft. And here are the values, very briefly, the values for the material for the resistance factoring approach. And here is the big victory, let's say the big achievement, because we have a harmonization and only VC1 will be applied. So this is a major achievement. We will not apply any more different design approaches. And here you can see the values of the gamma R values for the base and the shaft resistance for different type of piles, for compression and tension and transverse. Here for the transverse, it is not anymore harmonized, so we can use either VC4 or VC1. And here are the values for model pile method. The other one was for the ground model method. This is the same with different values for the model pile method. And here for the design by testing, again, gamma R values for design by testing, and the partial factors for pile draft. You can see here that we can use either material factor approach, both combination with VC4 and VC3, or the resistance factor approach with VC1. And there are different values for vertical resistance and combined axial and transverse resistance. Your colleague, Yorgo Belokas, tried to put all this together in the flow in several flow charts, and there are some flow charts for single piles, and this is very useful because, as you can see, it is quite complicated, and we will all need some time to get used to all this, and this kind of flow charts can be very useful for directing us to find our way in all those new concepts and how to find the proper values to be applied. So you will find those flow charts, including those for single piles, in the report of TGB2 for design examples that will be published next year. And also there is one for pile groups that Yorgos developed. So for SLS, of course there are some provisions. There is a permission to omit explicitly SLS verification if we have comparable experience or to apply a simplified evaluation. And there are some aspects regarding the SLS verification for pile groups and pile drafts. And as I said before, there are two other sub-clauses, implementation of design and testing. And the list of all the annexes related to pile foundation in Annex C. So, as I said before, we developed some design examples, and TGB2 in SE7 was in charge of this. And in this report I was telling you about, to be published next year by JRC and SEN, will comprise 25 examples. And for pile foundation there are 5 examples. One example for designing from static pile load test, another one using ground test results, meaning CPT, but deriving ground values, ground properties values, and use them afterwards. Direct, let's say, design based on CPT for a pile foundation in sand. Another example with pile foundation design from ground parameters, and an example on piled rough foundation. These are the 5 examples on piles. Oh, sorry, I forgot to omit this. We performed a benchmarking exercise with every country, and we received not many, but some results I would like to show you, because in fact it is showing what are the problems of the code and in the understanding of the code. Oh my God. So one of the exercises was the pile foundation design from static pile load test. So here you can see some of the details about the loads, the actions, and the static pile load test, which you can see here, and some of the assumptions. And for this, these are the values, the pile resistances for the 4 load tests. The mean value 2.04 meganewton and the minimum value 1.73. So in this case the correlation factors for the mean and the minimum are 1.1 and 1.0, and the representative value, it is computed like this. So now the design value, including the gamma RD, the model factor, and the gamma RC, the partial coefficient for compressive resistance, is giving us this design value. So now if we are determining the effects of actions, we can make the ratio between the actions and the resistance, and we are obtaining 8.2. That means rounded 9 piles. And I will show you now the results that we got from several countries. So here are the values. So not many, only 8 solutions coming from these countries. 9, 9, 8, 11, 11, 9, 9, 9, 10. Some of them applied a partial coefficient that doesn't exist. Some consider the resistance of a pile group, and therefore they obtain more than 9 piles. Some others use an old version of part 3, and some others get lost in the partial coefficient and use another one. The other exercise, so it was not clear for everyone which table with partial factors to apply, and they didn't see that this is depending on the method that was used for the determination of the bearing capacity. And we saw that depending on the national practice, the methods are not easily understood, especially those names which are not very relevant and not very clear. There was a second exercise for the benchmarking for the piles, those designs from profiles of ground test results. And this is the same example, so the same numbers as before. And here are the 4 profiles that were calculated with the calculated pile resistances from the model pile method. And here are the formulae that were applied, and we have to check the coefficient of variation, and this value was 13%. As I told you before, it has to be less than 12%. Therefore, the 4 tests were grouped into either 3 and 1 or 2 and 2. And for those clusters or those groups, of course, the coefficient of variation has to be less than 12%. So you have to split it in different zones. So considering 3 CPTs on one cluster and another one separately, we obtain these values, and I will not detail everything, just to show you the differences with all the model factors and so on. And here the final result is that 12 files are required. And let's see now the values that were provided by the different countries. We received 9 solutions, and there are some graphs here. So some of them split it in 2, 1 with 3 profiles and another one with only 1 profile. Some others didn't check the coefficient of variation and they put everything together. Some others put 2 and 2. So we obtain different values, including one who gave 15 instead of 12, 15 piles. So there is still a problem. People are lost in all those tables. So the final conclusion is that in every country we need to inform, we need to provide design calculation, we need to provide courses, teaching, whatever is needed, or guidelines in order to get used the people with all those new concepts, many tables, and it is a little bit confusing from time to time. So we will do this in Romania, and we are starting some courses and also some webinars about all this, and hopefully they will find their way. There is another task group called B1, which developed a report with case studies, real case studies solved using the new generation of Eurocode 7, and also those designers were young people. So these are developed by young geotechnical designers. And in terms of pile foundation, you will find in the report when it will be published, micropiles, combined pile draft with numerical modeling, and board piles with an analytical model. So it will be very useful to see all this. So I am coming to the conclusion, and I'm sorry if I completely so you need a toolbox, you need 4 documents to apply the geotechnical design for a geotechnical structure. This second generation is reorganized, revised, improved, and so on, together with new topics. There will be guidelines to be published, and I would like to inform you about this. There will be 4 guidelines. The first one, about the application of reliability concepts in geotechnical design, was published a couple of days ago. So you can provide, maybe Yorgos, you can provide the link because it is on the website of JRC, and it is in free access, so everyone can see it. There will be another one about the ground model, how to develop a ground model. A third one about the representative values of geotechnical parameters, and another one which was approved yesterday for the publication, about the implementation of design in execution. And there will be 2 other reports, the one with the simple design examples and the one with case studies. And all this, we hope, will be very useful for the users. So, Eurocode 7 Part 1 and Part 2 were already published. Eurocode 7 Part 3, it is still on vote, and the vote will end on the 28th, that means in 2 days. So we will have the results, the final results, and next year we will have it published also. We have to start the development of the national annex and of course of the translation into the national language. And the latest date for the elaboration of the national annex will be September 2027. And until March 2028, we have to withdraw all the former standards, national standards. And with this, I would like to thank you very much. And of course, I can answer to the questions that you might have. But there is something else, and I will put it on the screen. And I should present it, or Michael, you? Okay. We would like to inform you that on the 27th of March next year, at the Technical University of Civil Engineering in Bucharest, we will have our first Romania-Greece seminar on earthquakes and geotechnical engineering, with special guest speakers from Greece, George Gazetas, Kyriazis Kitilakis, and Yorgos Belokas, and 3 invited speakers from Romania, Radu Văcăreanu, who is a professor of seismical engineering in our university, myself, and another colleague of mine, Cristian Arion, and together with other contributions. So we hope that this will be very successful, and maybe some of you, except the 3 guest speakers, will come to Romania to attend this event. So thank you.